This video, I'll show you how to set up a model that does diffusion from a circular region. The geometry, it just consists of a rectangle and a circle. The circle is 0.05 meters in radius, and the rectangle is 1 meter across, just for the general scale. Now, to set this model up, I'm going to just really be interested in doing diffusion. So we'll have high concentration in this region, and it'll diffuse outward. To analyze this problem, I used a physics interface, transport of diluted species, and I'm turned off the convection here. And then diffusion, I need to specify the diffusivity, the diffusion coefficient, and I'm just going to use this value, which is a typical value for the diffusion through water. The no flux boundary conditions I'll keep for now as a default. That is the default, and I'll just keep it. And then initial values, I'll set this region to 0, and really the only thing that I did that wasn't just the default was I added this node for initial values. I selected the circle, and I make the initial value of the circle equal to 1 mole per cubic meter. Now, the mesh on this problem I made a little bit finer than the default mesh. I used two regions. This region I made extremely fine, and then the rest of it I'm making it finer. So when I mesh it, I get this density of mesh, and that seems to be sufficient for this particular problem. So I ran this out long enough so that this region decays, and I experimented around, but I looked at the basic scaling of the problem to get an initial time for the diffusion process, and then I experimented around in that vicinity. So we'll run it for 2 times 10 to the 7th seconds. And so this is really quite a fast model, and we'll take a look at what happens. The concentration looks like this after 2e to the 6th seconds. Right at the beginning, it looks like this. Let's see. So there's the initial condition, and you can see there's a little bit of a grading here right along the edge just from the graphics package. But then as we plot it at increasing time, the magnitude decreases in the circular region, and it increases out here in the periphery. And for this problem, we can go, it doesn't really take too long before this decays off pretty well to, let's see, 2.4 times 10 to the 6th, and we're down here at about 0.25 for the magnitude. Now, one thing I should point out is when I set this up, I set the let me see, where did I do this? I set the scale, the range of the scale on manual, and that prevents it from rescaling. If I were to uncheck this, then I would get a plot that looks like this. This shows it in a little more detail. It shows the distribution in a little more detail, but it's rescaling the maximum amplitude. So really just depends what you want. This is showing the distribution of the concentration using the initial scale, so it really shows how the concentration is spreading out. And if we take a look at this with a cross section that goes right through the axis of the circle, we see a plot like this. After 100 seconds, we have the blue plot, and then increasing time from green to red to light blue to pink. And pink is right at the end of the model. And you can see by that time, we really just have only a few percent of the initial amplitude here within the circle, and the mass is spread out to the outside of the circle. So let's see. One thing that will be of interest here is the distribution of mass. And so what I did was to, just a second, I set up definitions here that are the integrals of the concentration over different regions. Well, the integrals over different regions, and I'll use these functions to integrate the concentration. So under definitions, I used a 2D integration. I selected that region, that domain, and I called it circle, and then I made another one that I called outside. And then down here in the plotting, I used a global plot, and so I made a 1D plot group, and then I selected global right here. And because of these are definitions, I can access them through this global plot. I selected the solution 1 data set, and then I used the function names right here, the two functions, and then I added them up. So circle is the blue line, and this is the mass in the circle. This is the mass outside of the circle, and then the total. And so we can see that the mass isn't changing in the region. It remains the same, but the mass in the circle drops off pretty sharply. This is only, I don't know, a couple percent of the initial mass, but after roughly, say, 2 times 10 to the 7 seconds, 90, certainly 98%, 97%, something like that, of the mass is outside of the circle after that time. And that's shown by these integrals. Now we can do a slight variation on this problem by changing the boundary conditions. So what I'll do is I'll turn on this boundary condition here, this concentration boundary condition, and I've selected all 4 boundaries and held them at a concentration of 0. And so now I'll rerun the study, and this will do the analysis. And actually what I'm going to do is I'm going to increase the time a little bit. So let's go to 10 e to the 7th and run it again. And now by making a constant concentration along the outer boundary, what will happen is as the mass diffuses out, when it reaches the boundary, because I'm specifying the concentration at the boundary, that allows there to be a concentration gradient at the boundary, and it allows mass to diffuse out through that boundary. Okay, so what I'll do then is create another function. I'll just do this in post-processing, and I'll take the average over all 4 boundaries, and I'll use an expression here which is the magnitude of the mass flux. I got that by selecting this variable here, go to transport of dilute species, species C, and the normal diffusive flux, normal diffusive flux magnitude is what I selected. Let's just select this, the normal diffusive flux. Okay. So what we'll do now is to select evaluate, and what happens is this integral that determines the average is solved over this boundary, at all of the different times when the model has provided a solution. And here's the result. We can plot it, and the result looks like this. So what you get is this is the diffusive flux out through the outer square boundary. So for this time period, there's no flux out because the mass is diffusing outward from the circle, but it hasn't yet reached the outer edge of the square. But now it does, and it starts diffusing out through the edge, and we have mass loss at an increasing rate, but we have a finite mass within the square. So we get a peak diffusive flux out through the edge of the square, and then it drops off because we're losing mass from the center of the square. The gradient along the edge is diminishing, and it drops off with increasing time.